Hello and good day everyone, my name is Ron and let us answer some separation processes problems. Create an absorption column in DWC using the following data. The compounds are pure water, acetone, nitrogen, and oxygen using the property package NRTL. The inlet stream data is as follows, where the absorbent is just pure water. The gas inlet stream is a mixture of acetone, nitrogen, and oxygen, temperature and pressure, and then the number of stages is 12 and the column pressure is 14.7 psia or 101,352.9 newtons per meter squared or Pascal. So this is the given in terms of diagram form, and the required are what are the mass flow rates and mole fractions at the outlet streams. So to solve this, we must go to DWSim, create a new process model, wait for it to load. Afterwards, we will now set our properties. So the mixture or the compounds included are water and acetone, then nitrogen, and then oxygen. Alright, so the property package used is NRTL. So we'll click next and click here NRTL, add, and then the system of units is PSIA for pressure. We'll just go to C1 here and press PSIA or PSI. Fahrenheit for temperature, and then pound mole for molar flow rate. Pound mole for molar flow rate, and essentially that's it. Okay, so we'll set here finish, and to simulate an absorption column, as you can see here, there is an absorption extraction column, but it requires the Cape Open procedure. So I will simulate this problem using the Cape Open procedure. So in order to use the Cape Open procedure, you need to prepare the following data. You need to prepare your respective streams. So here is the material stream. Since there's a gas inlet and then there's a gas outlet, we put here the material streams. And we'll say here as the inlet stream is the liquid flows downwards from the top to the bottom. So we'll go here as liquid inlet or absorbent, and we'll go here as the gaseous inlet since gas flows from bottom to top. And liquid flows downwards, so from top to bottom. The bottom part is actually the liquid outlet. And here is the gas outlet. Alright, so we need to specify. So these outside streams don't need to be further specified. For the liquid inlet, we will stay here. We will specify it. So the inlet stream for the liquid inlet is an absorbent. Absorbent is just pure water. So that means that the compound of water in terms of mole fraction is at 1. That means the rest are 0. And here is 1, except. And then the stream conditions for this one specifically is 80 degrees Fahrenheit and 14.7 psia. Lastly, the molar flow rate of pure water is 176.4 pound mole per hour. So 80, 14.7, 176.4 pound mole for the gas inlet. So the compound amounts is not in fraction form given, so we'll just change these mole fractions into mole flows. So here, the water, there's no water here, so put here as 0. And for the acetone is 3.53 pound moles per hour. And for the nitrogen, 136.55 pound mole per hour. Then for the oxygen, it's 36.3 pound mole per hour. Click accept. And our total amount in terms of mole flows, 3.53, 36.55, 36.3, and 0 is 176.38 pound moles, and is already reflected here. Then 80 degrees Fahrenheit temperature, and pressure is 14.7 psi. And that's it. So that is the inlet and outlet streams. So there's no need to edit the outlet stream since that's what we want to find. So we go to Cape Open, press this one, drag it, drop, click OK, and here, then go to Cape Open Editor, wait for the load, and we'll change this into Simple Absorber and Stripper, change the unit name into Absorber, and the following data can be further specified down the road as we get our further editor open. Here you go. So since we are in the NRTL, we just need to remove this since this is its own respective property package, and there's no need to expose energy ports since we only want to know the amount of material going in and out in terms of balancing. For the title, no need. Components, no need as well. Operation, absorber, stripper, and the number of stages. What's the number of stages specified here? It is 12. So the stage here is 12 stages as follows. And that means that at the very top of the stage is the first stage, and this is where the feed 1 or the liquid feed goes in, and the second stage is the bottom stage or the 12th stage, and this is where the gas feed goes in. Afterwards, the properties, we'll go here, we'll search here Tekima and NRTL, since that's where it's specified as. Then we use Antoine and the ideal enthalpy reaction. And for the feeds, that's its specification analysis. Pressure, we will, according to our PowerPoint, the constant pressure is 101,352.9. 11352.9 constant pressure. Okay. Heaters, coolers, nothing to change here. Column specs and the results that is to be solved. We'll click save and exit. Afterwards, we'll now connect the respective streams. So since we know that the first stage is at the very top of the column and the liquid inlet must be at the first stage, then we'll click here as liquid inlet. And here at the bottom is the gas inlet. Alright. Afterwards, for the outlet, the top product is gas, since gas flows from bottom to top at counter current position. We'll say here as gas outlet for the top product. And then for the bottom product is a liquid outlet. There you go. And we try to force solve. And as you can see, there is an error we can observe. The error is because, according to the DWSIM, the NRTL, there's a missing interaction parameters for binary pairs of acetone and nitrogen. So this means that using NRTL, we will not be able to solve this certain type of problem due to some certain variable errors. And that's okay, because we cannot predict the amount of information already prepared in the DWSIM when compared to other simulation softwares. So in order to address this problem, in order to fully solve this problem, we will not use NRTL anymore. We will just use an ideal property package that we all know and love, which is Raoult's law. So going to settings and changing the thermodynamics from NRTL. So we'll just delete NRTL and go to Raoult's law. We'll add it. And now, Raoult's law is now being used for all streams. Then we need to also specify that in this property package, rather than we use the Tekima, we will now use Raoult's law, and everything is already automated. Same thing, vapor pressure is Antoine, and enthalpy is ideal. So click save, and we'll now solve the flow sheet, and bada bing, bada boom, the flow sheet is being calculated. It is still connected, and the flow sheet has been calculated successfully. So again, whenever the flow sheet did not calculate or solve successfully, don't panic. Double check the message from the simulator, DWSIM itself, and analyze what is going on. If the property package you're using does not account or cannot be used to solve for this problem, then just use another property package as long as it is within reason. So the NRTL compared to the Raoult's law, NRTL uses a more realistic approach in simulating real-life procedures of different chemical components. But in order to fully solve this problem, we'll just use Raoult's law, which is more ideal than real compared to NRTL. But it can still give a good estimate and estimate an answer to what will we be expecting as in value or output based on the given conditions in the problem. So in the gas outlet, according to the gas outlet, it has a molar flow of 178.297 pounds per mole and a mole fraction of 0.03 water, almost approximately 0 acetone, nitrogen is 0.76 and oxygen 0.20. For the liquid outlet, water is 0.98 approximately. Acetone is 0.02, nitrogen is 0.001, almost 0, and same in the oxygen, almost 0 as well. Moving forward, gathering the data from the DWSIM, which is this one, 6.1684 times 10 to the negative 10 gas outlet mole fraction of acetone, and the mole fraction of acetone liquid outlet is 0.02023, molar flow of gas outlet is 178.297, and molar flow rate of liquid outlet is 174.483. So how do we know if these answers are actually true? Well, we need to use some certain hand calculations. Before that, I would like to specify that we did not use NRTL property package again. We used Raoult's law. So that may be a certain factor on a certain difference in application. So this is, note that under the change of NRTL to Raoult's law, these are the values that we calculated. Because again, we did not use Raoult's law since there's a lack of data embedded in the DWSIM software itself. So to compare, let's solve this using hand calculations. So pre-solution for equilibrium, we need to find, so that due to NRTL not used in DWSIM due to lack of binary parameters, hand calculations will be based on what is the adjusted property relation, which is assumed to be Raoult's law. So remember, if you have solutions thermodynamics under your belt, you may find this equation very familiar. So this is the equilibrium relation of acetone A using Raoult's law, noting that the fugacity coefficient is actually 1 for the gas phase, and for pressure, it's at total pressure, while for the liquid phase, the fugacity coefficient is also 1. However, its saturation pressure is used in the F variable. Then equating both together to finding the relationship of y and x, we found out that this is the equation of acetone equilibrium relation using Raoult's law. Then, we need to find the saturation pressure of acetone at a certain temperature. So using the saturation pressure equation of Antoine correlation, this is the result. And using values from the book of Smith, Vanes, and Abbott of 8th edition CH160 Thermodynamics, table B.2, the saturation pressure at that specific temperature given is 32.9285 kilopascals or 4.7759 pounds PSIA, pounds square inch absolute. Then the pre-solution for equilibrium, we need to find the equilibrium equation of acetone. So using the equation derived earlier and substituting all necessary values and givens, we found out that the Psat over P total ratio is actually 0.3249, and we will call that as M, which is the slope of this relationship line. Then, how to find the mole fraction of acetone in gas inlet. So this is the equation. So the mole fraction is simply the number of moles of gas if acetone over the total moles. So this is what we calculated. Then we need to find the moles of entering inert water. This equation is given from the mole ratio equation. So the L apostrophe refers to inert water. Since we assume that the water is inert, that means it does not interact with any of the components, it just acts as a carrier or a conduit. That means that the amount of water going in is equal to the amount of water going out at the liquid outlet, and it does not go from liquid to gas. It is only in liquid form, meaning that this amount at water specifically stays the same. And this is the amount of inert water going in and out, 176.4 pound mole per hour. And inert air, we also assume that air is inert, meaning the air does not mix with water. So in this case, oxygen and nitrogen are components of air. In a sense, for us chemical engineers, air is 21% oxygen and 79% nitrogen. So knowing that, we use this formula equate it, and we have a inert air amount is 172.85 pound-mole per hour. So how do we compare it? So we use these values from DWSIM as additional parameters or values, and we will calculate the minimum stages required and compare it to the number of stages specified by the problem. So we assume, earlier we said that the problem requires us to equate it to 12 stages, and let's assume that to be the minimum stages. Then in order to compare if our values from hand calculations is similar to our values from DWSIM, we will also calculate the number of stages minimum using the data given in DWSIM and the data given in the problem. So in order to do that, this procedure, if you want more details on the procedure, you can refer to McCabe's book of separation processes. So to continue, the absorption factor at the top is this formula, and has 3.0451. The absorption factor at the bottom has this formula and this value. Lastly, the absorption factor using the geometric average. The geometric average absorption factor uses this formula, and this is the value, 3.0449. Then, how do we calculate the number of stages? Well, this is a shortcut equation. This is what we call the Kremser equation to find the number of stages, ideal stages minimum for absorption columns. So using this equation, Kremser equation, and since we already have the following data calculated and pre-calculated, we found out that using the Kremser equation, the stages given for our given problem should be 16 stages. So how do we compare further? So the difference between the calculated and the simulated in terms of minimum number of stages. So we calculate that the minimum number of stage using the DWSIM values should be 16 minimum stages. However, in the problem, it specified a minimum number of stages for 12. And finding the percent difference is actually 28.57%. Quite a large value. Well, the reason is because, a possible reason is because due to the sudden change in thermodynamic properties. Because the problem states that we should use NRTL. However, as you can see earlier, the DWSIM could not account for the NRTL parameters since it lacks certain parameters itself. Hence why I did engineering judgment and shifted my properties from NRTL to Raoult's law. So that may be a great source of variation on why there's such a large percent difference. There's such a large percent difference present in the comparison. Maybe the problem statement, apologies, it's not 20 theoretical stages, it's 12 theoretical stages. I forgot to edit it. This 12 theoretical stages, so let me edit it here now. Okay, sorry. So maybe the problem statement of 12 theoretical stages is actually configured as a true result of NRTL, as I said earlier. However, since DWSIM created errors when using NRTL, the change to Raoult's law showed a different result as seen. So remember, what the main takeaway for this is that DWSIM or simulators may pose a certain error whenever there are some parameters incomplete within their property packages built in. With that case, you must try to make your own sound engineering judgment to decide whether or not you should change to a different property package. I chose the Raoult's law property package because 1, it is easy to understand, and 2, it is a good estimate. Though not accurate to realistic conditions, it is still a good estimate. And given that it's only 28.7% difference, let us be grateful that it's not actually 50% or above 60% difference. That may be a cause of very, very double thinking type of answer. So that may be inaccurate. But since, as you can see here, 28.57, it's actually not bad in our case. So again, double check your properties. Be a good chemical engineer, have sound engineering judgment, and interpret what you must. So again, this is the problem. Thank you again. I'm Dayap, and thank you all for watching. Good day.